correlate data from here, as you know, galaxies are the red dots here, and that's correlated with the intensity mapping here on the right. So it's essentially the same, you look at the same physics, but here you look in detail, here you're looking as a diffuse measurement. That's not for hydrogen, that's for carbon monoxide, but the concept is exactly the same. And what do you want to get? From what's here, you try to extract from the neutral hydrogen, you try to extract the power spectrum for different redshifts, redshift beams, and on top of that power spectrum, you look for fluctuations. This is in the back, should be in the front, but these are small fluctuations that are superimposed in the fiducial H1 power spectrum, come as a very, very small amplitude fluctuations here, and that depends on the frequency range that you're measuring, frequency as a radio frequency. What comes for free is that once you set your telescope for a given frequency, you're setting the redshift interval you're looking at. That's straightforward. You have, for instance, for H1, 1420 megahertz as the rest emission of the hyperfine transition of hydrogen, and that when you redshift in space, you get lower and lower frequencies, indicating further and further observation. So measurements give you a direct redshift information. So, but to get that, to measure these fluctuations, which are tiny and which are behind a number of contaminants between us and the source of the hydrogen, you have to have a sensitive telescope. So we have kind of a wish list for a single dish H1 surveyor. So we need a large collecting area, so we need big dishes or many small dishes acting together. You need a large area covered on the sky. You need, for a single dish, low side lobes and very precise beam, because you don't want to collect contamination from outside your beam. And low side lobes mean that you will not get anything outside your optical axis. You need a long observing time because the signal is very tiny. And you need sensitivity for intermediate scales in redshift, where BAWG is important. The redshift range, which is interesting, is this. And the bias gets much larger after C equals to 1. And that's the frequency range you're looking at. So 1300 megahertz is 0.08 in redshift. 100 megahertz is 0.93. So I think all the radio telescopes we heard about today, and some we haven't heard about, they are, for hydrogen, they should be a little bit above this. If you have intensity mapping for carbon monoxide, the frequency goes higher. And down to here, which is very deep in redshift. What happens is that this frequency range, you have a lot of problems, including mobile phones, horizontal links, motors, all kinds of diesel motors, and other human-made gadgets that broadcast radio frequencies. So that's a problem. It's not astrophysics, it's a problem that we create, but we have to manage. Bingo meets all these criteria. So what do we have, what do we propose? We propose a single dish. It's a compact, but actually two dishes, a compact array with this focal length, this resolution for the optical system, 49-foot horns. They are sort of big. The horn is 4.3 meters, so it goes from here to the table, to the tip of the table. We have 49 of them, so a very large focal plane. So you cover this area in square degrees, so it's roughly 1/8 of the sky. We don't use cryogenics because it makes things much more expensive, much harder to control. That's the working frequency for bingo, redshift interval, channel resolution for the data analysis. What do we offer as a counterpart? We offer a simple design, so we don't move the telescope. It's a transit telescope. It's a single dish that looks at the same area of the sky. We don't have pointing capabilities. And we have most of the components off the shelf or developed for us in the Brazilian industry, so it's good. And the guiding principle is simplicity because we want to have it built as soon as possible. It's on the way. The status is, the horn prototype is completed and successfully tested. All the front end, all the parts from the horn to the receiver are built and tested. The receiver is built and tested with normal low noise amplifiers. I mean, commercial low noise amplifiers. The survey on site for contamination was conducted. That's why we chose that site, and it's being frequently monitored to guarantee that it remains clean. The optical design is completed. We have some legal issues with taking power to the site, having the cleaning of the area, which is handled by the University of Campina Grande in Paraíba and the local authorities. It's already granted. The terrain is granted. The working arrangements are done. So we are setting up a few details to start cleaning the area and building the structure. And we had a major project review in last July. Jacques is not here anymore, but Jacques was one of the reviewers. We got the green light to proceed to phase 2, which is good. We have 80% funded, and we are the 20% that's left needs the final engineering project for the construction. So after that point, we'll be able to proceed. It's interesting to say that we have federal money, not much, but we have federal money. And we have state money from São Paulo, which is about 80%. What are the challenges? Nothing comes for free, so we need to find a company to fabricate the dishes. We have companies who make 4, 5 meter dishes. We have some ideas on how to make a 40-meter dish, transport it to Paraíba, to the middle of nowhere, to assemble that as a dish. We have horns that work. The fabrication process is understood. We need to reduce the costs for 50 horns. We have some issues with the stability of the receivers, so we are looking for options. We use electronic skull fats or a continuous wave source for calibration. And we already have a plan for radio sources that are in the field of view for calibration. The receiver stability has to be tested with internal cooling. We haven't done that. It is stable for many hours in a row, but we don't have a day-night stability test in a controlled situation yet. The side lobe pickup is quite good. We had the measurements of the beam design, of the response of the horn. We need to have it assembled in the full telescope to see how the full system behaves. Individually, the parts work quite well. We have to keep that region quiet. We are working with the state agencies in Anatel, which is the regulating agency for telecommunications, towards transforming that area in a radio silence zone. And we are waiting for a clearance to have the Army Engineering Services to help us during the construction, roads, bridges, and terrain preparation. So, besides the baryon-acoustic oscillations, which I mentioned, that's why the name of bingo comes from, we have other science besides the BAWG power spectrum. We have matter density, redshift distortions, anisotropic BAWGs that we have changes across tangential and and radio BAWGs. We have the life history of hydrogen in the frequency range that we have, radio recombinations line in the galaxy, outside the galaxy, galactic continuum, mainly from synchrotron radiation and some from bremsstrahlung radiation. And of course, fat radio bursts, which will be a natural project for this kind of telescopes, except that we have a very big field of view for this kind of object. So we will not be able to pinpoint the location as BINGO is designed for now, but we will be able to have very good information on the energetics of the fast radio bursts. In the sense that we don't know where it comes from, but we can have the spectrum in very good detail, time detail. So this is a plot from Kovacs and collaborators from 2017. BINGO was mentioned, but at the time BINGO was moving from the initial site in Uruguay to Brazil, and it was not quoted in this, this review. So I did my own update of the plot. This page 44 of Kovacs et al. We are here. That's the angular resolution. This is the redshift interval. So we have no competitors in the band, except for sphere X and H alpha. Nobody else is working there, which is good, but that is a lot of responsibility because we are alone, we have to do well. We cannot fail against ourselves, right? So we have to do well. But the other thing is that we can cross-correlate with pretty much everybody else. So we can compare with all other measurements in the market. So besides radio, besides intensity mapping, so these are all for intensity mapping experiments. But we can also compare with radio surveys. BINGO is the blue strip here. That's deste, and this is the 6GF data, the pink one. So that's where multi-wavelength comes in. We have a good instrument with good data for multi-wavelength comparisons. And if we have S plus survey area, this is the BINGO area here, here, and here. We can also do something with Brazil leadership. So BINGO is being led by Brazil, and S plus has a very strong participation of Brazilian astronomers. So there would be a good chance of doing science for the let's say near redshift cosmology between 0.1 or 0.05 and 0.5. So this is the structure of our collaboration. We have a working group that's a telescope. Telescope is broken into antenna, receivers, digital backend, dishes, control cabin, cabling, which is a nightmare for the 50 horns that we have, data management, calibration, and then commissioning. This is what we are working on. We have this part here pretty much nailed down, except for the digital backend. We have all the plans for the control cabin. We don't have information yet, enough information for cabling. Data management, we have a data center at INPE that would be able to manage, but we have to contribute with the storage area. And calibration telescope commission is under discussion. The construction site, we have to deal with power supply, internet access, water security, road access, preparation, foundation, steel structure for the horns and for the dishes. One will be easy to place, will be on the ground. The other one will be in the vertical, and it will be hard. And we have to deal with the silence zone. The pipeline and science forecast has to do with the mission simulation, how the instrument sees the sky, separate components, I mean H1 from the rest, do a cosmological parameter forecast, do galactic science, transient object science, where fast radio bursts enter, and other science, which I mentioned, history, life of hydrogen, redshift space distortions, and so on. We have an outreach which is quite active. We are preparing a documentary on BINGO and the science that BINGO will deliver. Some press material is already out. Many interviews on YouTube and available. We have a group that works with internet and social media, and we have white papers on outreach. And that's the management structure that deals with, I mean, that's been done mostly at INPE. And we inherited this from the satellite program. So we are trying to have this as a major space project with all, the landmarks, the review process and stuff. It's much simpler than a satellite, but still it's large enough that this structure helped us a lot during this first major project review. So this is a quick sketch of the optical system. So that's follows the terrain inclination. We have the optical path from here to the horns here. That looks to center in the 15-degree declination. And that's, we are trying to finalize the focal plane positioning of the horns, but that's most of the simulation have come from this array, which can be expanded. You can have more horns in this part here, more horns in this part here, and more horns here. So we can get up to 59. So we can have 10 more horns with this structure. More than 59 will spill over to the outside of the secondary dish, and then it will not work. So that's the behavior of the pixels. There's a central pixel. It's very, very symmetric. So you see the cross-polarization behavior. That's the receiver structure. You have room temperature. So the horn is here. Here you have the polarizer. That's the magic tease, the orthomode transducer. So this is the main part of the receiver chain, and that's the digital backend that you do the Fourier transform of all the 280 megahertz frequency band. So that's another picture of the horn and the polarizer. And we are trying to finish this week the paper submission on the horn construction, horn testing. To the best of our knowledge, that's the largest radio astronomy horn ever built. We haven't seen the corrugated horn. There are some horns larger than this one, which are not corrugated, but the one with the grooves, the corrugation, is the largest that I've seen in the literature. So this is part of the testing process. That's the antenna facility at INPE. So that's an anechoic chamber. We have a transmitter facing this opening. Then we did a bunch of tests on that. I don't know if I'll be able to show you quickly. There are 4 very quick movies on horn, the horn fabrication. Let's see how it works. I'll have them all together. So we bend aluminum profiles to make rings, and we stack rings together to make a horn. That's how we were able to do something like that size without machining. So we have a machine that bends the profile that we want, and then we have a caliper, a template to guarantee that we have the tolerance that we need, and then we put together, checking the template with every single ring that's stacked. Since the horn weighs by itself almost half a ton, only this part weighs half a ton. With this part here gets to 600 kilos, we need a support structure, and that will be inside a hexagon structure that allows some movimentation to the outside and inside, horizontal and vertical for fine alignment. That's the sketch of the full structure. That's under fabrication. And this hexagon will become the horn array structure. So we will have something like that. We are still doing the engineering calculations to support that part here and see the tension flow to the sides of this structure, but it's very promising. So we will not have a building for the horns. We will have hexagon structure that will host every single horn. Oops. So this is a very quick overview of our data analysis pipeline, which starts with the 2 minutes. I will go quickly here. So we go here. That's a general pipeline. Sky, instrument, simulate the mission, have a time-ordered data, remove the data, prepare the maps, and start doing the science after you extract each one here. Karin Fornazier has a poster on this part here on the outside. So we have a forecast for the foreground that's being recalculated for bingo. So we have a simulation that's 2019, 31 horns, the minimum that we expect, 1 year observation. The estimated survey sensitivity is 41 microkelvin for 1 year observations, 31 horns. This is the input of H1, this is the output, and then you have the power spectrum, which is, where is it? Which is here. Then you have the input is the blue, the output is the red. So we need some improvement at smaller scales, angular scales. That's the budget. We are talking about foregrounds which are 4,000 Kelvin, and we have someone that's 0.1 Kelvin. We have to work it out. Quickly, I will not go in details to the bingo site, but we are somewhere in Paraíba here. That's the state. We will be here. That's the area when it doesn't rain. That's the RFI survey. That's very clean. That's a site in São Paulo where we have other radio telescopes. These are mobiles. This is aircraft. This is mobile. This is a church that has a TV station that transmits here. So you also pick them. These are airplane routes, and these are geostationary satellites that contribute to pollute our data. So we are working for the man-made horizontal data. We are working on a silence zone. So these are the requirements. We are working with the state company, with the federal agency. And I want to close with this here. That's the review board report that was issued to us. That was prepared by Zulema Abraham, Rodrigo Leonardi, Jacques Lepine, Jeff Peterson, and Steve Torchinsky. They are our committee. And they said that we have an important milestone in the life cycle. Some aspects are still at the preliminary phase. We have to work on them. If the project management succeeds in delivering and operating the bingo radio scope, we have a huge potential for delivering competitive science. So that's so we are concerned about this. We have to work a lot on this, but we have green light to have to receive the rest of the funding. So these are the bingo players. We haven't won anything yet, but we hope to win very soon. So INPE, USP, Universidade Federal de Campina Grande, University of Manchester, UCL, University College London, Yangzhou University in China, ETH Zurich, Switzerland, EIS in France, KwaZulu-Natal in South Africa, and Universidade de la República. So we have 3 of the 5 BRICS here. So that's it. Thank you.
Any question?
Is there any possibility that you already thought about it, estimating magnetic field using the H1 line?
That's likely because we'll be able to measure a circular polarization. I think we can transform that and have the magnetic field of H1, yes. I did mention, but we don't have a full polarization analysis, so we don't have LR-RL. We would need 2 times more receivers, but we have LL-RR and a circular polarization, so we'll be able to be in the game.
Okay. It looks like the jet lag won over everybody about now. So thank you very much again, and thank you for all the speakers.
Thank you.
And tomorrow we start again here at 9 o'clock. Thank you. And please don't forget to tell your colleagues back home that that they just have to look for the CBPF YouTube channel, and they can watch all of